Hello everyone, my name is Peter Ray. Welcome back to the RE7 channel. Today we are going to build something exciting and very close to real industrial practice. In this lesson, we will learn how a hydraulic robotic joint is designed, calculated, and controlled using Python as an engineering calculation tool. By the end of this video, you will understand how engineers define real project input parameters, how hydraulic cylinders are sized, how pump flow and motor power are calculated, how a servo valve controls a robot joint takes, and how Python helps automate all these engineering calculations. This is exactly how modern industrial electro-hydraulic robot systems are designed. So, let's begin. Project overview. Imagine we are designing a 6-axis industrial robot for a manufacturing factory. This robot must lift heavy mechanical parts and move them accurately. Because the loads are heavy, we choose hydraulic actuation, since hydraulics provide very high force density and reliable industrial performance. Our goal in this project is to design one robotic joint powered by a hydraulic cylinder, controlled by a servo valve, and calculated using Python. This is not just theory, this is exactly how real hydraulic robot joints are built in industry. Project overview. Understanding the engineering inputs. In real engineering projects, we never start by choosing a cylinder directly. We start with task requirements. For our project, the required inputs are payload mass equals 120 kilograms. Arm length from joint to load equals 1.2 meters. System hydraulic pressure equals 250 bars. Cylinder stroke equals 450 millimeters. Extend or retract cycle time equals 3 seconds. Safety factor equals 1.5. These are typical project specifications given by a client or production requirement. Our Python program will use this input to calculate joint torque, required cylinder force I, cylinder, bore size, oil flow rate, pump flow. Pump motor power is hose diameter. This workflow matches real hydraulic design procedure. Step 1. Calculating load force. First, we calculate the load force created by the payload. In physics, force equals mass multiplied by gravity. So in Python, we calculate load force equals payload times gravity times safety factor. Gravity equals 9.81 meters per square second. We multiply by the safety factor to ensure safe operation. This gives us the real force the joint must handle. Step 2. Calculating joint torque. Next, we calculate the torque required at the robot joint. Torque equals force multiplied by distance. So, joint torque equals load force times arm length. This tells us how much rotational effort the joint must produce. In our example, this gives approximately torque equals 2117 Nm. This is the rotational torque that our hydraulic joint must generate. Step 3. Calculating cylinder force. Now we connect mechanical torque to hydraulic force. In real robot arms, the hydraulic cylinder is connected to the joint through a lever mechanism. For simplicity, we assume the cylinder lever arm is 1/3 of the robot arm length. Cylinder force equals joint torque divided by lever arm. This gives the force the hydraulic cylinder must generate. For our project, the cylinder force is approximately cylinder force equals 7,056 newtons. This is the push or pull force produced by hydraulic pressure inside the cylinder. Step 4. Calculating cylinder bore diameter. Now we size the hydraulic cylinder. Hydraulic force comes from pressure multiplied by piston area. So, force equals pressure times area. From this, piston area equals area equal force divided by pressure. Once we know piston area, we calculate bore diameter. Diameter equal square root 4 times area divided by pi. Our Python program performs these formulas automatically. For our example, cylinder bore diameter equals 60 millimeters. This tells us the real industrial cylinder size we would choose from a manufacturer catalog. We also define cylinder stroke equals 450 millimeters, which matches the robot joint travel requirement. Step 5. Calculating oil flow rate. Next, we determine how much hydraulic oil must flow to move the cylinder in the required time. Cylinder speed equals stroke divided by cycle time. Then oil flow rate equals flow equal piston area times speed. Python converts this into liters per minute. Step 6. Calculating pump flow rate. Our robot has multiple joints. If we assume 4 joints operating simultaneously, the total pump flow is pump flow equal flow per cylinder times number of cylinders. For our design, pump flow equal 48 liters per minute. This value is used to select the hydraulic pump in the power unit. Step 7. Calculating pump motor power. Now we calculate how much electrical power is needed to drive the hydraulic pump. The standard hydraulic power formula is power kW equals pressure bar times flow, BL divided by mean divided by 600. Python performs this automatically. Summary of Python outputs. After entering project inputs, Python automatically outputs torque equals 2117 Nm. Cylinder force equals 7056 newtons. Cylinder bore equals 60 millimeters. Rod diameter equals 35 millimeters. Pump flow equals 48 liters per minute. Pump motor equals 20 kilowatts. Hose diameter equals 12 millimeter. These results match real industrial hydraulic design values. This is exactly what a hydraulic engineer would calculate manually but now automated by Python. In this lesson we have defined the real engineering inputs, use physics and hydraulic formulas, build a Python calculation tool, design a real electro-hydraulic robot joint, connected theory to industrial practice. This is exactly how modern hydraulic automation projects are developed. Thank you for watching the RE7 channel. If you found this lesson useful, don't forget to like, subscribe, and leave your comments below. In the next lesson, we will build the full Python graphical interface and simulate the servo control loop. See you in the next RE7 engineering lesson.